current theory states that, okay, it all crunches down and becomes a point, like singularity. But that's where quantum gravity is coming in and trying to explain what actually happens, what the singularity actually is. But yeah, some of them is they're also considering the possibility that it could be a fundamental particle that it forms.
So what I was thinking is, why should light have the highest speed in the universe? All the contradictions arise from the fact that, okay, first an event has to happen and that information has to reach you, and then all the other things can follow. But that is just for your cognitive processing. But what if we take out that fact like completely away from the argument? There's no life, there's no processing, there's no cognition, there's no perception. Now it's just particles and matter and processes and radiation going away from it. Why does light have to be the fastest thing? Hey Curiosphere, this is Pratham.
And I'm Suraj.
So on this channel, we discuss our thoughts and have a deep talk on an intriguing topic to see where the conversation takes us. So for this episode, we decided to do one of our favorite topics, which is black holes, and I'm sure a lot of you find it really interesting as well. I know Suraj and I have discussed this quite a bit, sometimes here and there, and found it really fascinating from what's possible to what we know. So on this episode, we're going to discuss things which are some of the biggest black holes in the known universe, which range from like 66 billion masses of our sun to perhaps the end of the universe, where we might have to live by a black hole and harvest its energy in order to survive. But before we get into all of that, I kind of wanted to talk about one really fascinating thing about this whole thing, whether it's been from the beginning or while watching movies like Interstellar, or just, watching some YouTube videos or reading about it or talking to you about it, is what is inside a black hole, right? And that just takes me from theory to practical to so many things. So what do you think is one of the best possibilities of what is inside a black hole?
Oh, hold on. I think that's a really heavy topic right there. So before we delve into it, I feel, it's better that we discuss the basics of it. So, so this is how the formats of the episode's gonna be. We're gonna discuss a few basics of the black holes, like what's a black hole, how is it formed, how is time affected near it, and event horizon and stuff. So for the folks who are already familiar with it, feel free to skip around this time. And if not, enjoy the black hole basics with us. So let's get started. So let's start with what a black hole is. So what you're seeing on the screen right now is an artist's depiction of black hole. So to describe it in layman's term, it's a region in space which is so dense and has such strong gravitational pull that not even light can escape it. And whatever light streaks that you're seeing right now, it's actually the accretion disk, which we'll delve into later. And it's not the light that is inside of a black hole. So basically that cannot come out and it will not come out. So this is just matter around black hole that's orbiting around the black hole. So that's what a black hole is.
And I wanted to also say a little bit about how it is formed. So in layman's terms, basically a black hole is the corpse of a star. Once a star which has enough mass has died and collapsed, and it has so much gravity that it can't hold itself up any longer, it collapses into a black hole, and basically it becomes this really super dense remnant of a star which pulls everything towards it. And like Suraj said, basically not even light can escape. So surrounding the remnant of the star is basically a kind of virtual sphere in which the gravity is so strong that everything kind of gets pulled towards it. So that even if a photon is passing by that region, it'll get pulled into that core, and it will not be available for it to reflect and bounce off and reach your eye for you to be able to see it.
Yep. And one of the most interesting effects of black hole, because of its such high density, is how time is affected by nearby it. So to understand that, we must understand space-time fabric first. So Einstein tells us that space and time are not actually two different things. It's woven into a single fabric called, unsurprisingly, space-time. And whenever there's matter, it always distorts space-time around it. So even we human beings can distort space-time, but it's so insignificant that its effect doesn't matter. But if you take objects like Earth or Sun, now we're getting somewhere. So these are so massive that space-time distorts and forms a curve around it. Now, around a black hole, the distortion of space-time is very extreme. And this leads to very interesting effects. So basically, if you're near a black hole, time kind of runs slowly for you relative to an observer outside the black hole. So when I say outside the black hole, I mean outside the effects of gravity of a black hole. Alright, so for many people, this is a bit hard to believe. Like some people don't even believe that time can run differently. But if you think about it, we currently exploit those facts to our advantage over here. So just a simple example is that if you think about GPS satellites, because it's far away from the Earth, the gravitational pull on GPS satellites by the Earth is weaker compared to the gravitational pull of Earth on us. So because of this fact, time runs differently for GPS satellites compared to us. So if you just take a look at your phone, the time that shows you, it's coming from those GPS satellites. And for that to happen and for that to be correct, it has to be pre-corrected based on Einstein's general theory of relativity and then sent to us. Otherwise, we'll be off by a lot of seconds in a day, and that just accumulates over time, and like we'll all have very different times. So yeah, this stuff actually happens, and near a black hole, it's very extreme. So to summarize, as you're approaching black hole or any other objects of extremely high density, gravity is so strong that it has distorted the space-time in such a way that time starts slowing down for you and it almost becomes zero.
Also, what I wanted to speak about is the event horizon. So like you mentioned, around anything which has a lot of mass, there's a gravitational field. So as you get closer to the object, the field increases, becomes stronger and stronger. And the same goes with the black hole as well. As you go towards the core of the black hole, the gravity increases. So the event horizon is basically in that field when you reach a point close enough to the black hole that the gravity is so strong that you can't get back now. There's no way you can escape. So basically a point of no return. And that's the same distance from the core in every direction. So basically you can imagine it as a sphere that's around the black hole, which is called the event horizon, beyond which, like if you step past the event horizon, you won't be able to get out of it. Now you're just going one way down and that's all there is. No other way out. So yeah. Yep. And that's basically why we see the sphere as a black hole, right? Because nothing can escape, like you said. But yeah, also what I just wanted to touch upon before we end this intro segment is what we do really see, right? And what we see is generally a black sphere or a ball. And around that we see this kind of orangish or reddish light. And that is basically an accretion disk, which is something like when matter accretes or collects around a black hole. Since the black hole is spinning and the matter also would probably be kind of spinning and spiraling into the black hole. And the black hole has an axis and it's spinning on that axis, like along that axis. So when the matter kind of spirals in, it forms this plate around the black hole, which is called an accretion disk. And because of the friction and the heat, that matter might start glowing and have light coming off of it. And that's what we basically reaches our eye and we see as an accretion disk.
Yep, that's true.
Yeah, so I think that kind of should get you up to speed on the basics for anybody who's watching who's not very familiar with some of these concepts. And some of the animations, if you're listening to us on YouTube, will help for sure. So do check that out if you want to. Okay. So now that that's done, so what I wanted to ask you before we get into some of the questions we talked about at the introduction is that do you know about when this concept of black hole was kind of first theorized or thought about?
Is it 20th century?
No.
No? So
Yeah.
19th?
So, not really.
Oh, damn. Enlighten me.
Yeah. So, Yeah. So a couple of 100 years back, more than like 300 years back or something, there was a scientist. I'm not sure of his name. I think it was John Mitchell. But basically, the concept actually came about when there was this understanding of gravity after Newton introduced it, right? And so there were tests performed and there were things being theorized, and people started thinking about the velocity needed to escape, right? And like, let's say you kind of shoot something into the sky, it reaches a certain velocity and then it kind of falls back down.
Yeah.
So people started thinking about, okay, that's related to the gravity and how much force is holding that object back down, or the field that's pulling the object down. And so people started thinking about that. And there was, there were thoughts about, okay, what if Earth had a stronger gravity? We need more force to thrust something thrust something into the sky. And then this scientist thought about this and said, what if there's an object that no matter how much force you use, it will not be able to achieve that escape velocity. Like for Earth, we have an escape velocity. But similarly for a star also, he theorized that, okay, there might be an escape velocity. But what if the star's gravity is so strong that that photon or any particle would not be able to escape it? And that was the actual first thought about something like a black hole, even though all this space-time and all those notions that came in with Einstein later on, those didn't exist at that time. But like, you see how he just used that escape velocity concept to, just...
Yeah, theorize.
Yeah.
That's such an
Yeah. So I just wanted to touch upon that, like, because something like that, which is so complicated, has so many parts to it, and you can come to it from any direction. And as soon as they kind of figured something about gravity and escape velocity, they'd reached it already. And it's only later that it kind of became such a big phenomenon.
Yeah, that's actually crazy, because I thought that it was only theorized after Einstein came up with his understanding of space-time as one single fabric. And then we started thinking about black holes as some things that can actually be there in our universe. But it's crazy to think that even from Newtonian gravity, this thinking emerged.
Yeah. And it's not just like the escape velocity part. He thought that, okay, no photons will be able to escape, so it could be a star which will not be able to actually give light out. So...
Oh.
Yeah.
Yeah, that's pretty wild. Just to think, just from Newtonian gravity, they came up with that.
Yeah. That's why I wanted to bring it up, because a lot of people don't know about this. And when I first heard it, I thought it was pretty fascinating.
Yeah, it definitely is.
Cool.
So now actually going off in a tangent, I just wanted to address one misconception that people generally have regarding time slowing down near black holes. And I know it's very hot and juicy topic to talk about, how time slows down near black hole. But what actually happens is that your perception of time will remain the same. Like if you're near a black hole, you won't suddenly start moving in slow motion, or your clock won't start ticking slowly. But what actually slows down is time relative to an observer outside the effects of black hole. So if he sees you, like if you're near a black hole and if he's far away and he sees you, then he'll see that you're moving slowly and your clock is ticking slowly and even your heart is beating slowly. So that's the only thing that's going to change. For you near a black hole, nothing's going to change. It's exactly like if you're in International Space Station, you will still move the same way compared to if you're on Earth. Except that you have zero gravity over there, of course. So because of this effect, right, a lot of cool things are possible. Just like on Interstellar, where I think they're on Miller's planet, I guess. Yeah. So a few hours over there is 51 years. It was 51 years on Earth. So this leads to a lot of interesting sci-fi stories where, you can go into the future relative to others' future, just by going near a black hole and orbiting it maybe once and just coming back. But technically, you actually don't need a black hole. You can go near any high massive stars or like neutron stars or like supermassive stars. And also if there's a black hole, it definitely helps. And now we know that there are black holes, like supermassive black holes, at the center of every galaxy. So, and I hadn't appreciated how big supermassive black holes were. the normal black holes are like around a few hundred times the mass of our sun, and these supermassive black holes, it's ridiculous. It's 66 billion times the mass of our sun. It's
pretty crazy.
Yeah, those numbers are almost, it's inconceivable.
Sure.
Like, they don't mean anything to us. Like, if I say 10 million times the mass of our sun or 66 billion times, like, we can't perceive that difference, but it's ridiculously high density objects. But yeah, it's pretty crazy. So yeah, if you go near those black holes, I think by the time you come, I don't know if there will be Earth to come back to.
So one more thing that really like kind of fascinated me when I first learned about it was the Schwarzschild radius, which basically, which kind of tells that anything can really become a black hole as long as you squeeze it into a small enough volume so that the density goes really high. So for example, you, me, this this phone or camera that we're using, or anything, or the Earth. If you squeeze the Earth to like less than like almost like a groundnut or a peanut size, it would become a black hole, because so much matter and mass is being squeezed into such a tiny volume. And there's like, we have a formula for it discovered by this German scientist Schwarzschild. So yeah, that was pretty fascinating to me. And I never really thought that, because I always thought, okay, stars will become black holes, or at the center of galaxies we have that. But I never really thought that, okay, anything can become a black hole. So it's more about how you distort that space-time, instead of more about what, like, you don't need any specific type of matter or specific process to happen. It's just, as long as that exists in that space-time, it will just start sucking in
Yeah, that's true. Yeah. And do you know, like, I actually calculated the Schwarzschild radius for me. Like, I put my
for you specifically with your weight.
Yeah, exactly. I plugged my weight into it, and apparently you have to compress me to a point where it is 10 to the power minus 25 meters. That's ridiculously small. A proton is, I think, 10 power minus 15, and you have to compress me
15.
Yeah.
Okay. That's pretty crazy.
Yeah. So a proton is around 10 power minus 15. And you have to compress me to around 10 power minus 25 to turn me into a black hole. Yeah, that's pretty crazy.
Okay. Yeah.
And for the Earth, like, if you can compress the Earth to the size of a peanut, then it becomes a black hole.
Yeah. Here's a question for you. Like, this is also something that I came across before. And I kind of fell for it. I didn't realize. But what if for you guys, like, if y'all can answer this, what if you replace the sun with a black hole of equal mass? What do you think will happen?
I know the answer.
Okay, go ahead.
Yeah, pretty much nothing. If you're just talking about the effects of gravity. But if you're talking about like all this photosynthesis and the other effects of sun, then that's gonna change. But in terms of gravity, if it's equal mass, then nothing much happens for the gravity.
Yeah, pretty much, because the field is going to be the same, so Earth is going to be revolving just the same way it usually is. And I mean, of course, things will get dark suddenly. Yeah, things will start dying. Things will get cold. It's going to go for one particular end. But it's just like, as far as the Earth revolving, it'll just continue to revolve as it is. So that's pretty cool. That's something people don't realize, because for gravity, only thing that really matters is the mass. Yeah. So
So actually, speaking about that, it brings me to a very interesting observation that I made. Yeah, I think it probably is pretty evident to you and to many others, but it wasn't to me. So when you say that you replace Earth with an equal mass black hole or any other star, like, it would remain the same, right? So, but if you change the mass, right, it would definitely have an effect on Earth, basically. Basically the orbits of the Earth. So let's say you either increase or decrease it, and you immediately replace it. But to feel that effect, it won't be instant. It will still take 8 minutes. So I was under the impression that it was only the light that traveled at the speed of light, any photon that travels at the speed of light. But it's also the gravitational waves that travel at the speed of light. So basically it's information. Information cannot break this speed barrier.
Yeah. So basically that the gravity field of the sun is like it's a field, so that, like, let's say if the sun suddenly disappeared, the wave that carries the information that the sun has disappeared, so the earth doesn't have to revolve around it anymore, would take the same amount of time that light takes to reach the earth.
Yeah.
So yeah, I know what you mean. So that actually also makes me think about something that I recently was wondering, and it might go off in a little different direction, but this is just like my thoughts on it. So what I was thinking is, why should light have the highest speed in the universe? So the reason I was thinking about this is basically because, like, see, when you look at it from a fundamental perspective, these are like electromagnetic radiation. It's not like particles with mass. So, and the practical aspect of it is, I mean, one is that the mass converts to energy and there's that transaction happening. But if you think about it, it's just like for us to perceive, for living things to be able to see and perceive, right? But what if there were no living things? What if there was nothing living that was there to perceive it? Then why does that... You get what I mean, right? Like, all the contradictions arise from the fact that, okay, first an event has to happen and that information has to reach you, and then all the other things can follow. But that is just for your cognitive processing. But what if we take out that fact like completely away from the argument? There's no life, there's no processing, there's no cognition, there's no perception. Now it's just particles and matter and processes and radiation going away from it. Why does light have to be the fastest thing in the universe?